Okay, so there's no homework to check. Uh, how many people at least started their take-home quiz? Yeah, good. No, you know the answer. About halfway through? Okay, that's good. Um, so yeah, I'll click that tomorrow unless you want to get rid of it today. So what I want to do today, we're going to do one like multi-part problem, and then I'll let you work on this little review. We'll start reviewing early for this one. But for the do now, I need to see if you guys can translate from words into symbols the statement that I have up there. Sometimes they don't just give you the differential equation. Sometimes they just give a bunch of words, and you got to be able to translate it. And we're going to be talking about texting monkeys later. Like yelling in the background. Oh, we're recording. All right. So, who thinks they can translate this sentence into symbols? The rate at which the volume V changes. Let's start with that. How do we translate that, Cameron? dV dt. The rate at which anything changes is d that dt. Okay. So we got that. Now we're up to the word is. How do we translate the word is? Equals. This is the part that usually gets picked. Directly proportional to. What if? How have we seen that translated? Oh, well, okay. You said kr. Okay. Well, the directly proportional to just means some number times, and the number we tend to use is just k. So it equals, it's directly proportional to. Whenever you see that, just write k times. And then, yeah, the square of the radius, not square root, the square of the radius would be r squared. Because it says, if you go through step by step, so underline in red, that's dv dt. Is this your equals? Directly proportional to some number k times, might be 1% of or whatever it is, and then the square of the radius. I just want to get in the habit or just get used to translating from words to symbols. Okay, we're not doing anything with this. Okay, so today we're going to tackle an AP-like question, but I made it, so it's a little weird. All right. Monkeys can text, I'm sure. There's some texting monkeys somewhere. You saw that gorilla Coco? She had a vocabulary. How many words? Coco? No, it was like she does talk. And she would say little things. Um, well, they're talking about Coco the gorilla, but we're back to talking about texting monkeys. So anyway, at the beginning of 2012, there were 100 texting monkeys. Perhaps you know a few. The increasing function p models the population of texting monkeys. Experts estimate that p will satisfy the differential equation dp dt equals 1/20th times the quantity p minus 50 for the next 25 years. P is measured in monkeys, and T is measured in years from the start of 2012. So we have basically the derivative of this function, but we can't draw what P of T looks like. We know that P is some function of T, the population of text. But basically, we do know what the population is at time 0. Do you see what that is in 2012? That's 100, right? So we know it starts out at 100, but we really don't know anything about this graph, right? We just know its derivative is dp dt equals 123 minus 15. Yes, p at time 0 is 100. We could write that up here if I can reach. So the population at time 0 of monkeys is 100. Okay, so this question, it's going to start out with some oldies but goodies. We're not going to do anything right away like we've been doing recently. I'm going to kind of bring it back. So we're going to start out by writing the equation of the tangent line to the graph of p at t equals 0. How do we write the equation of the tangent line to the graph of p at 0? And I don't want specifics. I just want, like, in general. Well, Jillian, you had your hand up. What were you going to say? You would say y? P of 0. That's how you get your y1. Good. Anytime you have to write the equation of a tangent line, you're going to have to, they'll always give you the time, or in this case, it's the time, but the x coordinate. You have to get the y by going to the original function to get your y1, and to the derivative to get your slope. Okay, let's see. So we're going to have to get these two values, the population at time 0, and the derivative of the population at time 0. Well, how about the population at time 0? It's 100, right? Now here comes the tricky part, if you can call it tricky. We have to get the derivative when t equals 0. If you look at how that derivative is defined, it's not defined in terms of the time. So I want to figure out what is dp dt. I want to evaluate it when t equals 0. Bless you. What do I plug in for p? I know it's when t equals 0. I want the derivative 100. Because at t equals 0, the population is 100. Okay, so there's the slope of our tangent line. All right, so what do we get if we simplify that? 2.5. I'm going to write 5 halves. I like my slopes look like fractions. Okay? And then the x minus 2 is just x. So we could leave it like that, or we could add the 100 to the other side. So the equation of the tangent line to my population graph at time 0 would have the equation y equals 5 halves x plus 100. You can kind of picture it there, But that's just the tangent line. We don't know the actual function. Okay, so now we've written the equation of the tangent line to our population curve at time 0. And they want us in part B to use this equation to approximate the population of texting monkeys when t equals 1. So we want to approximate the number of texting monkeys 2013, so when t equals 1. We're going to plug, what are we going to plug into the tangent equation? 1. We plug it into the y or the x? The x, right? Because basically we said y on the population curve is roughly equal to y on the tangent line. So we just plug the 1 into the x of our tangent line. How many little texty monkeys do we have? 100 and... Say it, Emily? You had, I think. 102.5. So there's one little monkey. Maybe he's not so good at it. Maybe he can only... I don't know. I don't know why he's, he's like that. Right, 2.5. A little baby texty monkey. A little amputee texty monkey. Something. Maybe he does it. I'm just saying. They have people, or not maybe not people, but animals maybe gnawing off their limbs or things. I don't know. It's rough out there. Okay. So far, we've done something we've done before, but it's in the differential equations problem. Because, see, guys, this question on the AP exam is almost always the last free response question. It's a no calculator question, and they'll throw in other stuff. And I was trying to think of all the other stuff they could throw in this question. The big points are going to come from separating and integrating, but we want to be ready for the other stuff. Okay, so let's see what else. Aha, what is that? Find, what is that? Oh, the second derivative. So the second derivative. So that's the derivative of the first derivative. Well, the slope of the tangent line. So we want the slope. We want the rate at which the slope of the tangent line is changing. Yeah. Well, what was the first derivative? So it is the derivative of dp dt. So we're trying to find the derivative of. You don't have to write this. I just want to make sure you see where that. Remember the notation where it comes from. The first derivative is 1/20th p minus 50. Okay. So we got to take the derivative of that. But here's the kicker. And every year I warn the kids. I'm going to warn you too. It's with respect to t. So if you take the derivative of t with respect to t, it's 1. But if you take the derivative of any other variable with respect to t, it's something dt. Holy moly, you knew where I was going. What do we do? Yes, it is implicit differentiation. Actually, mackerel. I should just sit down and let you guys go, because you know this. I know you could. All right, so now I got to take the derivative of 1/20th times p minus 50. What do you want to do? You want to distribute? I got no problem with that. You know, it's a constant multiplier. You could leave it there or distribute. I'm fine with distributing. Going with the flow. So 1/20th p minus 5/2, right? Because it'd be 50/20th. All right, so got to take the derivative. Can't avoid it forever. So, derivative, you know what, guys? I'll take the derivative of the 5/2. All right, you just worry about the first term. What is the derivative of 1/20th p with respect to t? 1/20th? dp dt. Aha. And then the derivative of 5/2 is 0, so we don't have to worry about that. Now, we know what dp dt is, right? So it's 1/20th of, this always happens with these, 1/20th times p minus 50. No, I'm not stuttering, I'm substituting. Right? We got 1/20th dp dt, but this, right, is equal to this. I just substituted in, and I have to do that because sometimes they'll say find the second derivative just in terms of p or t. This time we actually have to find the value of the second derivative t equals 0. So I didn't want to leave it like that. What's 1/20th times 1/20th? Which is it over 40 or 400? Right. You know, I'm hearing all sorts of things. Kids are yelling odd numbers from the back of the room. I don't know where that's coming from. All right, so it's 1 over 400 times p minus 50, or p minus 50 over 400. That's the second derivative. What? You want to work out? You want to do that px 90? I don't think you can do it in 50. I think it's 90. All right, so now this is not the only thing. So we got the second derivative, but they want us to evaluate it at t equals 0. Should I just pretend that that's a p and plug 0 in for p? No. Yeah, when t equals 0, p equals 100. They want to know. You got to put the p in there. That's accepted. All right, what is that going to equal? 50 over 400. 1/8. So all that to get the second derivative to this population graph at time 0 is 1/8. Because when t is 0, remember that p equals 100? Yeah, that's what we're plugging in there. Kids at home, we put 100 in there. Okay. Now, usually after you find the second derivative, this is such a classic pattern. You approximate a functional value with a tangent line. Then they ask you to get the second derivative where you drew the tangent line. We got it. And now comes the question. Hey, remember that approximation that you found before? Do you think it's an under or an over approximation? Somebody's right. Yes. Why do you think that this was just a random question, part C? No. Why did we find the second derivative where we drew the tangent line? What is that telling us? We found it was second derivative, Cameron? Concavity. And we got a positive 1/8. So what does it mean about the concavity? Concave up. So where we drew that tangent line to our population graph at time 0, we just found out that it's concave up there. We drew a tangent line at t equals 0 to a graph that was concave up. So what does it mean about our approximation, under or over? Under. Well, now you have a reason. You were just guessing me. Oh, that was a horrible tangent line. Can I grab that? Yes. Oh, yeah. Well, it's supposed to be tangent at 0, but that's good. So, yeah, if we plugged 1 into the equation of our tangent line, all right, so that number that we got, 102.5 texting monkeys, that's a little less than the actual. Okay, so we say it's under, all right, because the second derivative was positive, so the graph of P is concave up. It is concave up at t equals 0. That was a fun little trip down memory lane, all this old stuff. What do you mean she's cutting? Really? Okay, now comes the new stuff. And this will be like 5 points out of the 9 points. I wouldn't mix it with all those other things. They'd pick a couple things maybe. Now they actually want us to find the particular solution, P or P of t. P of t looks more fancy. Maybe at the end call it P of t so you know it's a function. But we want to solve for P, the population, as a function of time, starting with that differential equation and the points 0 and 100. So tell me the first step to find the particular, separate. All right, go ahead mentally or on your paper, separate the variables. Separated and really integrating, aren't you? All right, did you separate yet? Separate the variables because it's just multiplying and dividing to separate them. Yeah. whole point just for separating the variables. Yeah. So never just look at it when it says solve, the differential equation. You better separate. So we can divide each side by p minus 50 and multiply each side by dt. You might say, well, 1/20th, that really could be on either side, but when you're trying to solve for p, you want that side to be as clean as possible. Any other constants you want to put on the independent variable side. How's the separating, all right? Okay, so after you separate, what do? Okay, that's a little bit. What are you getting for the left? It's just an ln. We don't need to put in anything up here to have the derivative of what's down there. We already got a du over u, right? So you don't have to write out what u equals or anything like that. You just say it's the ln. And again, with these problems, these differential equation problems, the argument what's inside is positive, so we don't deal with the absolute values. So p minus 50. Ooh, what about the other side? Nice! 1/20th t plus c. I was expecting 1/20th x. And even that would have been good. Don't get me wrong. I know a lot of people like to get the c right away, but when you have to exponentiate, always do that first, or you get some. I don't know. It seems like it doesn't work out right when people do it the other way. They get confused. I don't know what you think we're talking about. They just said to divide by ln. You can't do that. Spell exponent. And then I-A-T-E. Yeah. So when we exponentiate, what do we get on the left? Okay, this is my way. I have to move this. P minus 50. C times E. Nice. All right, we're getting there. Let's just move that 50 over, then we'll get the C. So P is equal to C E to the 1/20th T plus 50. And we could have got the C. All right, so that we know that when T is 0, the population is 100. So we're going to plug those numbers in. What do you have for C? Yeah, it's 50. Because e to the 0 is 1, so we have 100 equals C plus 50. Go up to the step right before you plug the number in, and then just replace the C. So I'm going here, I'm going to write P equals 50. If you didn't do this first, and you go up here, then add the 50 afterwards and get it on the other side. 50 E to the 1/20th T. Now, that is the population at time T. I like the function notation. So instead of just calling it P, I'm going to call it P of T. It looks more fancy. It shows you that, function. So the population at any time T we can get. Which leads us to the last question of the day. Mushrooms. Before we approximated the population of texting monkeys at T equals 1, now we can actually find it. Let's see how good our approximation is. This you would need a calculator for, because I made this up. I wasn't really thinking that kids would need this calculator. So we would plug 1 into our population function. Our approximation was 102.5, but we said that might be a little under because of the concavity. Let's said. I know, but you have more of a monkey. It's less disturbing to look at now. Maybe. Maybe he's just fur grew out for the winter. It's. I don't remember what it is. I know it's a little more though. About a 6'4". Right, a little better. So our approximation was a little under. We were right. How fun is that? Okay, so for the rest of the period, you guys are just going to work on this review sheet. If you can get through the first 6, it would be nice. We're getting a dent in it early. Just try to do the first 6 tonight. You can do as much as you want. Yeah. Ooh, you're ready to do it. That's a good idea. Okay, I'm stopping this bed.